This is question 4 of the midterm for spring 2025. The title of the problem is ASLR Mod 5, Memory Safety. So immediately we know that we're looking at a memory safety problem. We also know that because we have some C code, a stack diagram, and some GDB output. And so the first thing to note is that we have three functions that we're looking at. We have exploit, shfn, and main. So that's very cool. But before we even look inside the code, let's just get started on the first question, because the first question is just asking us to fill out a stack diagram. So looking at the stack diagram template that we're given, we're starting at main and we're going all the way into exploit, and the bottom half looks like local variables of exploit. So we're not really thinking about shfn just yet. So to start off, right below SFP of main, we know that there are no stack canaries enabled because it says right here, all other memory safety defenses are disabled. And so we're just going to be looking at local variables of main. And we can see that there is one right here, a function pointer called shellcode. This syntax is kind of complicated, but just know that shellcode is the name of this variable. And we know that's the only local variable that's defined inside main. So we can sort of call that right here, shellcode. And because it is a pointer, we know it's 4 bytes, so it's only taking up that one spot. We also know that this question is asking us to look at the stack when the program is paused at line 5. And so line 5 is inside exploit, which means we have to step inside exploit. And looking at the stack template, we know that we're missing the RIP of exploit right here, above the SFP of exploit. And then the next thing we can see is that we have a bunch of what looks like local variables, and the one that we're missing is between buff and new byte. So buff is right here and new byte is right here, and the one missing is k. And so let's just go find the answer choice that has shellcode, RIP of exploit, and k, which would be answer choice B. And that is part 1. Moving on to part 2, what is the value of the RIP of exploit, assuming the program is still paused on line 5? So remember that the RIP of a function is where the instruction pointer will return to once that function returns. And so what that means is it's going to be somewhere inside the code part of main. And so luckily we have the assembly instructions of main disassembled right here. And we can see that right after exploit is called, right here we have just another assembly instruction. And so this will be the RIP of exploit because this is where the machine will return to after exploit returns. And so 080760CC is our answer choice, which is question C, or answer choice C. So the next two subparts provide, we want to provide an exploit that causes the program to execute shfn. So now we can get into the nitty-gritty details of our C code. And the first thing to note is that, one, we have two inputs right here, fgetC, which is taking in a character, and fgetS, which is taking in a string. And it's being put into new byte for the character and buff for the string. The next thing to notice is that we have this big while loop right here, which seems to be writing to buff the value of new byte. And so these two inputs are kind of being integrated inside here. So let's go look at the first part first. So we see that fgetC is getting a new byte, and there's nothing really to look at over there. The next part is fgets, and we can see that this one is taking in 21 bytes. And remember that fgets, the last byte, is always a null terminator, which means that what we're really doing is putting in 20 bytes into buff, and then ending it with a null terminator. The problem that we can see immediately is that buffer is of size 16 bytes, which means that if we're able to write 21 bytes, then we're overflowing buffer, which is very useful. Looking at the stack diagram, 5 bytes above buffer include the SFP of exploit and the least significant byte of the RIP, which is very nice. The problem is that because fgets places the last byte as a null terminator, we're really only writing a null terminator to the least significant byte of RIP so far. So let's look at the second part of the C code, which is this while loop. We're writing a new byte to some parts of the buff, and those some parts are defined as n times k for all values less than buffer length. And the buffer length is just the length of the buffer, and if we fill up the buffer, that should be 21. Sorry, it should be 20, because the 21st byte is a null terminator, and that's not included in the length of the string. So k plus equals 1 for all for values of n equals 5, which means that the indexes that we're really writing to, so the values that n times k are equal to, are 0, 5, 10, 15, and 20, and that's it. And 20 is okay because we have a less than or equal sign right here. And remember that the 20th index of buffer is the 21st byte of buffer, which is the least significant byte of exploit. And so if new byte is the value of the least significant byte of RIP that we want, then we're able to put that in. So let's remember that the end goal of this exploit is to execute shfn, which is over here, but thankfully we have a function pointer to that function, and that lives in the stack right above the RIP of exploit. And so what we really want to do is move up the RIP up to where the shellcode is. And so we can kind of do that with a ret-to-ret exploit. If you remember from question 7 of project 1, using a ret-to-ret exploit effectively pushes the RIP up the stack 4 bytes for every ret that you put in. So if we put a ret inside the RIP of exploit, then the shellcode, which lives right above the RIP of exploit, will be the effective RIP, and it will return to execute that code. So we want to have a ret instruction address inside the RIP of exploit. And we can see inside our GDB output, we do have a ret instruction address. And we can also see that from part 2, this is very close to the RIP of exploit, which is right here. And so the only difference between these two addresses is the least significant byte. And we want the least significant byte to be DC. So to wrap this all up, what we want to do is sort of write DC, 0xDC, into the least significant byte of exploit, of the RIP of exploit, which means that we want a string of length 20 in order to maximize the number of bytes that we can write up to the last byte of buffer. And then the byte that we want to write is 0xDC. So the value of new byte should be 0xDC. So the first part is provide an input to fgetC. So remember that that is the value that's going into new byte, which we want to be DC. And then fgets, which is the initial value of buff, we want that to be any string of length 20. So I'm going to use A's for garbage bytes and just put 20 of them. Cool. Moving on to the next part. How many different values of the variable n would result in the correct exploit without modifications executing our shellcode? And so remember that n, the role of n here is that the bytes or the indices that we're able to write to are just factors of n that are less than or equal to 20. And we can see that because we've been able to write to 0, 5, 10, 15, and 20 when n equals 5. And so all of the possible values of n are just the factors of 20. And so we can kind of list those out. 1, 2, 5, 10, 20. I'm missing one here. I'm missing a 4. And so we have 6. So the answer is 6. Moving on to the next part, which is which memory safety defenses, when enabled alongside non-executable pages, would cause the correct exploit without modifications to fail. So the first option choice is pointer authentication codes. Because we are overwriting the RIP to a pointer to ret, we would need to create a valid pointer to our ret instruction, which we're not really able to do And so PACs would cause us to fail this exploit. The next choice is stack canaries. So remember from the stack diagram that there are no stack canaries and this function and our exploit works. The stack canaries, when enabled, would live between local variables and the SFP of main. So there would be one right over here between buff and the SFP of exploit. And because that stack canary is 4 bytes long, this would cause us to miss the RFP of exploit. Would have full write ability onto the canary and only the least significant byte of the SFP of exploit. And so that would not work. So stack canaries would prevent us from completing the exploit. So the next question is, which modifications to the program itself would prevent the correct exploit without modifications from executing SHFN? So very similar to the previous problem. We can look at these each one by one. So the first option is to change the fgits count from 21 to 17. And remember that 21 was very important because that allowed us to write to the least significant byte of RIP. With only 17 bytes, we can only write to the least significant byte of SFP. And so this would not allow us to exploit or not allow us to execute SHFN without changing our code. Next choice is changing line 8 to int bufflen strlen. So this is changing the type of this variable, but because the value of the length of the string is a very small number, we're not really able to exploit the fact that we have a unsigned to signed integer conversion here, and so we can't really do anything with that. The next option is changing line 10 to, instead of a less than or equal sign, to just a less than sign. Remember that this would stop us from writing to the least significant byte of RIP of exploit because we need n times k to equal to 20, and when buff lane is 20, then n times k will not equal to 20. So this would stop us. And then the last one is changing line 12 to k plus equals 12. So remember that k is used to multiply n. And so the values of n times k would be 0, and then 5 times 2, so 10, and then 5 times 4, 20. And because 20 is the one that we care about, this would still work. So moving on to the last part, it wants us to assume that ASLR is also enabled and asks us what is the approximate probability that the correct exploit without modifications executes SHFN. And so we have a clarification that happened during the exam that ASLR also randomizes the code section. What that means is all of the segments of code are being moved around, but also remember that relative addresses stay the same. And so if we're looking back at our exploit, what's really happening is that we're overwriting the least significant byte of the RIP of exploit. And so when ASLR is enabled, that value that we want will change. And so because we're only writing a singular byte, we have to guess that one byte. And there are 256 valid values of a byte. And because only one will actually work, our answer is 1 over 256. And that is question 4 of Spring 2025's midterm. Thank you.